Hello again from the Telecommunication Systems Laboratory. We are here next to our VNA, millimeter wave VNA, and we're actually measuring and testing our SPAR antenna for our project. So this is a 3-element dielectric resonator SPAR antenna. As you can see here, it has 3 dielectric resonator boxes. The center one is the active box, and we have 2 parasitic dielectric resonator boxes up and down, and they are placed on a ground layer, as you can see here, and there are some slots underneath the boxes through which we actually feed the dielectric resonator box with the RF signal. So this is the backside actually of our second prototype, so you can see a better look of the design and the control circuit at the backside. Here, as you can see, we have the active feed line, so we have one active element with one active feed line here, and the tiny SMPM connector. We deliberately chose this connector because of its small dimensions. It's definitely more convenient for the placement of the component. And then we have the control circuit, 2 feed lines for the 2 parasitic elements, and 2 control circuits with 2 pin diodes. You can see here 2 tiny black chips, IC integrated circuit chips. It's the 2 pin diodes, on-off pin diodes. So through which 2 pin diodes we actually adjust the mutual coupling between the parasitic element on the other side and the active element. Here, of course, we don't have the dielectric resonator boxes, so you can see the 3 slots where the feeding actually takes place, and some stencil marks in order to align the dielectric resonator boxes correctly. So here we are testing our first prototype. We placed the 3 dielectric resonator boxes on our ground layer, and we are actually feeding, we have 2 power generators in order to apply the correct voltages to the 2 pin diodes, to the control circuits at the back side. And here we have both pin diodes off, and you can see the both side, let's say, state of the antenna, and you can see the reflection coefficient, the S11 response versus frequency, with a quite good bandwidth. It's around 3.5 to 4 gigahertz bandwidth. It's a really good bandwidth. And so if I turn on one of the 2 pin diodes from the bore side pattern, I will actually switch the pattern to a specific direction, and if I turn on the other, I will switch the pattern towards the opposite direction. Of course, we cannot see that on the VNA, but we can see when we turn off and turn on the pin diodes, we can see a small change at the S11. So if I turn on the first pin diode, here you can see the change. So now I turn on this pattern, which means that the pattern, this pin diode, and so the pattern now is switched towards this direction. And if I turn on the other pad, here you can see again the change on the VNA. Now the pattern is looking towards the other direction. So we have 3 antenna states, both sides, up and down directive beams. And also we have an alternative, let's say, bore side when we turn on both. So when we turn on both pin diodes, we get again an alternative, let's say, bore side state of the SPAR antenna. We can see here from the VNA response, the reflection coefficient is quite good. It has a very satisfying matching, and goes below minus 25 dB. Quite good bandwidth, over 3 gigahertz, probably 3.5 gigahertz. The only problem and the most significant deviation that we have from the simulation is the fact that the antenna is resonating at a higher frequency. If we place the marker, I think we are about around 28.3 gigahertz at minus 27 dBs. We believe that the main reason for that, the higher resonating frequency, is the fact that the density of the fabricated electric resonator boxes is not perfect. And when I mean perfect, is 100% density that we were using in the CST simulations. We tried several 3D printing methods and approaches. We tried several 3D printers. This is so far the best that we got so far, but we're gonna do an additional round of 3D printing and try with some reverse engineering, let's say, go back to the simulation and do the simulations with a lower density. That's the whole point. Instead of 100% density of the dielectric resonator boxes, we're gonna use a 95% density, because the lower density, it means a smaller electric permittivity, which gives a higher frequency. That's the only significant deviation from the simulation results. Other than that, we are quite happy. We have a very good matching, impedance matching, and a very good bandwidth. And it seems that we also got the 3 states, as you can see, from the abrupt changes of the S11. So we are quite happy that it works fine.